Hello again, welcome back. This is our first video lecture for Chapter 7, Video Lecture 7.1. The title of the chapter, Kinetic Energy and Work. So right there in the title we see we're going to have two brand new concepts for us in physics, kinetic energy and work. The reading that goes along with my video lecture here is Chapter 7, Section 1 on kinetic energy, and there'll be another section I'll mention in a minute. But first, let me try to give you the big picture for this chapter. We're still studying dynamics. Remember, dynamics is all about explaining why a particle moves the way it does. And in some sense, we introduced the physics that we needed in Chapter 5, Newton's laws of motion. The three of them, with Newton's second law being the most important. And from Newton's laws of motion, we can, in principle, explain why a particle moves in any what would be called classical situation. So why do anything else? Why introduce new things like kinetic energy and work? Well, let me try to motivate why we're going to do this. There might be situations where a particle is moving under certain conditions, but to apply Newton's second law to describe or explain the motion of the particle would be very mathematically complicated. And if we could come up with some new physics ideas, but still gets at the same goal of explaining why a particle is moving, but would be easier to use than Newton's second law, that could be very helpful. And that is the whole point of the next two chapters. Introducing new physics concepts to help us explain why a particle is moving. That will be an alternative set of tools in our physics toolbox, alternative in addition to Newton's laws. Let me show you with a little Wiley Plus animation a physical situation I'm thinking about where Newton's second law would be challenging. So what this picture shows is a water slide in a water park. And the red dot way up at the top on the y-axis at y equals 12 meters represents a child, which we're going to treat of as a particle, that's going to slide down the water slide and down into the water at y equals 0. And we're just going to first run the animation so you can see the child, the red dot, slide down the slide. There will be an arrow in red that will represent the child's velocity vector, which will be tangent to the slide and getting bigger in magnitude. Okay? Seems pretty simple enough. The child slides down the slide. Notice the shape of that slide, though, is somewhat complicated. It's got some curvature to it. It's steep at first and then it levels out. That is a somewhat complicated mathematical surface for the slide. Now let's say our goal would be to calculate how fast the child is moving when she gets to the bottom right there. What is the magnitude of her velocity vector? All we know right now is to try to apply Newton's second law. But to do that, A equals F net over M, I've got to pick coordinates, and I've got to find components of forces, and I've got to try to solve for A, and then figure out how fast the child is going at the end. Let me show you now the forces. I'm going to turn on the force vectors. Basically, this is a free body diagram for the child. That's the blue arrows that you now see. The downward one, of course, is F grav, vertically down. And what is the other blue arrow, force-wise? You know the answer to that? Notice it's perpendicular to the slide. And if that's true, no matter where the child is on the slide, it must be the normal force. Is there a friction force, you ask? No, we're going to neglect that because it's a water slide, so friction is minimal. But my point is that as the child slides down the slide, although F grav is constant and always pointing straight down, Look at what's happening to the normal force. Oh, now all of a sudden it's getting bigger and bigger and bigger, and of course it's changing direction to stay perpendicular to the surface. Look how complicated that normal force is. Wow, look at that. That child is really going to feel that force. But the point is, in terms of solving Newton's second law here, that normal force is very complicated as the child moves down the slide. To try to apply Newton's second law to this, it's going to be a nightmare. Yet we sure would like to be able to calculate how fast the child is moving at the bottom of the slide. The ideas in chapters 7 and 8 are going to enable us to do this kind of problem, to deal with this kind of situation. Okay? So that's just my motivation for why it's worth learning some new ideas. Okay? All right, now back to our slides. So let's start in this section introducing or talking about a new physics concept. It's called kinetic energy. But before we can even talk about that, to say we're going to talk about a concept named kinetic energy begs another question. What do you mean by just energy? Kinetic energy must be some specific form of something called energy. What do you mean by energy? Let's take a step back. All right, so here comes my description. Notice it's not a definition, it's just a description of the concept in physics known as energy. It may surprise you or it may not to learn that that's a pretty tricky thing to describe well, the concept of energy. And so I'm going to be reduced to telling you somewhat vague description. And we're just going to have to learn with practice how to employ the different forms of energy correctly. So here's my description of what energy is in physics. First, here's a good thing. It's a scalar quantity. In physics, energy is a scalar quantity, i.e., not a vector. And whereas a vector quantity has a magnitude and a direction, a scalar is a quantity that has no direction and is just represented by a number. No direction to energy, no components. It's a scalar. That should make us happy, right? So energy is a scalar quantity that specifies important information about the state of a system. Told you it's going to be a little bit vague. Important information about the state of a system. Notably, the ability of the system to cause change in physically measurable properties of its environment. So it's telling us something about the ability of the system to cause change. And that's about as good as I can do right now. Okay? But the key thing is it's a scalar quantity. That's already a hopeful avenue of thought. If we can introduce new things, how about we use scalars? All right. Now, whenever we introduce a new quantity in physics, we have to figure out what its SI unit is. The SI unit of energy is called the joule. Capital J is the symbol. It's named after James Joule, a British inventor/engineer who was impactful in the improvement of steam engines back at the beginning of the Industrial Revolution. So James Joule is the person, but the SI unit is called the joule. As far as we're concerned, energy comes in three basic forms. Forms of energy. The first we're going to learn in Chapter 7 is called kinetic energy. I'm going to define that very specifically in just a moment. The next form we're going to learn about in Chapter 8 is called potential energy. A bit more abstract than kinetic energy. That's Chapter 8. But I will just give you a preview. For us, potential energy will be in three forms. Gravitational potential energy, so-called elastic potential energy, and then next semester we'll study something called electrostatic potential energy. But they're all forms of what a form of energy called potential energy. And the third basic form of energy is called rest energy. You'll learn about that if you take Physics 280. And there what we're referring to is the famous equation E equals mc squared. That's called the rest energy of a particle. It's the energy a particle has because it has mass m. That came to us, of course, from Albert Einstein. We're not going to talk about rest energy this year. Here's something else to know about energy, this scalar quantity called energy. It's got these three basic forms, and the energy can be transferred from one form to another. As far as we're concerned in this class, the transformation will be between kinetic and potential, those two forms. Okay? Kinetic and potential, back and forth. Transfers can happen. Here's an important experimental fact that we've learned from many, many, many experiments over hundreds of years. We can't prove this next statement, but we have never found an experimental or observational violation of it. And this observation is, the total energy of a closed system cannot change. Closed means closed from outside influences, separated from the outside world. If a system is closed, separated from the outside world, then the total energy of that system can never change. That is an experimental fact that we have observed to be true. Okay, with that somewhat vague description of energy, let's get to our first definition of a form of energy, and let's now be specific once we start defining things. So the form of energy that we're going to talk about in this chapter is kinetic energy. And that's the form of energy a particle has because it is moving. It's all about motion. The energy a particle has merely because it's moving. Here comes the definition of it. We're just telling you the definition of kinetic energy and the formula you should use to calculate kinetic energy. All right? First, note the symbol for kinetic energy, capital K. Then note the three lines here. That means we're defining kinetic energy. And here's the definition. Take 1/2 of the particle's mass and multiply that by the product of the x component of the velocity squared plus the y component of the velocity squared plus the z component of the velocity squared. That's the definition of kinetic energy. Note, however, that if you take v sub x squared plus v sub y squared plus v sub z squared from the Pythagorean theorem, that part right there is just the magnitude squared of the velocity. So another way to write this is 1/2 times m times the magnitude of v squared. Please note, though, that this notation means vx squared plus vy squared plus vz squared. That's what that means. We have to always remember the first way I've written it, because that's really what it means. And these second ways I'm writing it is just shorthand, because we're a little bit lazy. And yet, if we're going to be even more lazy, let me show you another way you'll see it in the books. Just 1/2 mv squared, and we'll often just say that. What's kinetic energy? 1/2 mv squared. But please remember, we're being a bit sloppy when we write that, or say v squared. Because what we really mean is that in the first expression, vx squared plus vy squared plus vz squared. We mean, when we say v squared, we mean the speed squared. We mean the magnitude of the velocity squared. Okay, I'm going to do a little mini practice with you here in just a second to emphasize that. That's the definition of kinetic energy. What's the SI unit of kinetic energy? Well, look at the definition. It involves mass and speed squared. So the unit must be kilogram, and then for speed squared, meter squared times second squared. Let's just rearrange those units a little bit. I'll do that right below. Kilogram times meter over second squared times, and then I have one factor of meter left over. That's just the same thing. I write it that way because this combination, kilogram times meter over second squared, we learned in chapter 5, is called the unit Newton. So my point is that the unit of kinetic energy is equivalent to Newton times meter. Newton times meter. But wait a minute, way up above there, I said the SI unit of energy is joule, J. Kinetic energy is a form of energy, so it must be joule. So what I'm saying to you is that the unit of joule, the SI unit of energy, is equivalent to the unit of Newton times meter. And you'll see it written both ways, Newton times meter or joule. All right, here's a little mini practice that I want us to do together. Okay, I'll write it down over here. Just right here in the video together, us together. Suppose I tell you that I've got a particle and it's got a mass of 2 kilograms. And at a certain instant in time, its instantaneous velocity vector is 3 meters per second times I hat plus negative 4 meters per second times j hat. Question: what is the kinetic energy of this particle at this moment? I would like you to stop the video, pause it, do the calculation for yourself, and then come back and we're going to compare. Okay, did you do the calculation? I really hope you did. It's good practice. Let's go through it together. Let's calculate the kinetic energy. Let me give myself some room. First, let me emphasize that this number right here in the velocity formula, multiplying the I hat, 3 meters per second, that's the x component of the velocity, v sub x. This number in the parentheses multiplying the j hat, negative 4 meters per second, is the y component of the velocity. This is why we like unit vector notation for vectors, because it's very easy to read off the separate components of the vector. All right, with that in mind, let's use the formula for kinetic energy. Let me clear up some of my marking here. And let me emphasize that the form I want to use is right here. 1/2 times the mass times the product of the squares of the velocity components. That's the safest way to do it. So K equals 1/2 m 2 kilograms times Vx squared. Well, Vx is 3 meters per second, so squaring that is 9 meters squared per second squared, plus Vy squared. Well, Vy is negative 4 meters per second, so you square that. Of course, it's positive 16 meters squared per second squared. Note, kinetic energy can never be negative, ever. By its definition, by its formula. There's no way to get a negative result. Now, what do you get here? Well, 9 plus 16 is 25, and 1/2 of 2 is 1, so you get 25 kilogram meter squared per second squared, which is joule. That's it. We just used the kinetic energy formula to calculate the kinetic energy of a particle for the information I just gave you. Okay? All right. So as long as you remember to use the correct expression for V squared, kinetic energy is pretty straightforward to calculate from this definition. Okay? All right. Now, in this video, I'm going to talk about one more important topic that we will need for the rest of Chapter 7. I didn't need it yet, talking about kinetic energy, but we're going to need it from now on. So I'm going to now introduce this new idea. It's actually an idea from Chapter 3, the chapter on vectors. So we're going to go back in the book, and now there's more reading that you can go to for further explanation. It's Chapter 3, Section 3, which is all about multiplying vectors. And the key idea we're going to talk about now is what's called the scalar product of two vectors. I like that name, the scalar product, and I'll explain why I like that. But for those of you that have studied vectors before, you may have also heard this called the dot product of two vectors. All right, let me explain to you. I'm just going to tell you how it's defined for now, and then we'll end up using it in a next following video. So the picture you see here shows two generic vectors. They're labeled little a arrow and little b arrow. They can represent any kind of vector quantities whatsoever, and they don't have to be the same type of vectors. A could be an acceleration and b could be a force. Or A could be a velocity and B could be a force. Or A could be a displacement and B could be a force. Or A could be a velocity and B could be a displacement. They can be any vectors whatsoever. And they're also drawn as arrows, and they're drawn tail to tail. Or like I often say it, they are drawn with a common tail. Their tails are together, okay? And when they're drawn with a common tail like that, it's pretty clear that you can talk about an angle between them. That's that arc right there. And we're going to use the symbol, that's the Greek letter phi. Phi is the angle between A and B in this drawing when they're drawn with a common tail. This is an important picture, because I'm going to talk about now the scalar product of those two vectors, A and B, and how it's defined. Ready? I'm just going to tell you the definition of the scalar product of two vectors, A and B. Note the notation. A arrow dot B arrow. That's how the scalar product is denoted. And because of that dot between them, that's why it's often called dot product. 3 lines, it's defined to be. Right? The definition of the scalar product of two vectors is, take the magnitude of one of the vectors, the first one, A, times the magnitude of the second one, B, times the cosine of that angle phi between them. Right? Phi is the angle between A and B when they're drawn with a common tail. Angle between the two vectors, in this case A and B, when they're drawn with a common tail. That's the definition of scalar product of two vectors. Okay? All right, now here comes some important points about this definition that it's very worthwhile understanding. First, the right side of this equation contains only scalars, right? Magnitude of A, scalar. Magnitude of B, scalar. Cosine of an angle, scalar. Right? So the product, the result of this is a scalar. So I've taken two vectors and I've done a kind of product to them, and the outcome is a scalar. That's why I like to call it the scalar product, because it's reminding me of what I get out when I do this product. I start with two vectors, A and B, and I do this particular kind of product to them, and the output is a scalar. Okay? Now, that scalar could be a positive number, could be a negative number, it could even equal 0. It depends on the sign of cosine phi. But please note that that sign does not indicate a direction. The outcome of this is a scalar. Scalar doesn't have a direction. All right? So whether or not A dot B, the scalar product of A and B, is a positive number, a negative number, or maybe even equal to 0, all depends upon that cosine phi part. Is cosine phi positive? Is cosine phi negative? Or is cosine phi equal to 0? Here you would be served by remembering what you've learned about cosine. Cosine is, you probably learned this in high school, trig. Cosine is positive in the first quadrant, negative in the second quadrant. And in a special case, when the angle is exactly 90, cosine of 90 is 0. So, let's do a little summary here. If phi is between 0 and 90, including 0, cosine phi is positive. And so your scalar product will be positive if the phi, the angle between the A and the B, is between 0 and 90, including 0. If phi is greater than 90 and up to and including 180, then cosine phi is a negative quantity. And the way I do the scalar product, I'll never need to go above a phi of 180. If phi is exactly 90 degrees, then cosine phi is 0. So again, just to be clear, the first statement right there would correspond to a slightly, would correspond actually exactly to the picture I've drawn there with the A and the B, because the angle phi between them in that drawing is clearly less than 90 degrees. So for the A and the B as they're drawn in this diagram, that scalar product A dot B is going to be a positive number. Let me draw a second picture to correspond to my second bulleted item that I've just put the bullet by. If phi is greater than 90, but less than or equal to 180, then the cosine of phi is negative and the dot product is going to be negative. Let me just draw them over here to the side. That would correspond to, well, something like this. B would be like that. There's the common tail. And maybe A would go off like that. So that the angle between them, when they're drawn with a common tail, there's the phi, is clearly larger than 90 degrees. Then the scalar product of the vectors drawn like that would be a negative number. And if, special case, but it's important, if the A is exactly perpendicular, put the little right angle symbol there. If the A is exactly perpendicular to the B, so that the phi equals 90 degrees, then A dot B, so now I'm doing this case down here, is equal to 0. Very important to remember what you know about the cosine when you're working with scalar product. Okay, here's something that people wonder, so we might as well just state it. You'll get the same result for the scalar product if you use the larger angle between the vectors. In other words, go back to my original picture up there. Instead of the red arc labeled phi, use 360 minus phi, the big angle all the way around like that. You get the same answer. Why? Because cosine phi and cosine 360 minus phi are equal. However, I personally will never use that larger angle. I see no reason to do it. I think it's just confusing. But that's a point to know in case you were wondering. The product is often called the dot product because of that dot. And we often will say A dot B, or sometimes even A dotted into B. But its formal name is scalar product of A and B. The scalar product is commutative. That is to say, you can do A dot B or you can do B dot A. Doesn't matter which vector you write first. The answer doesn't depend on that. Here's a geometrical interpretation, at least that's how I describe it, of scalar product. Geometrically, what is scalar product telling you about two vectors? It is telling you this: the product of the magnitude of one of those vectors with the component of the other vector along the direction of that first vector. And the component of one vector along the direction of another vector is sometimes called the projection of the first vector along the direction of the second vector. So the scalar product is, take the product of the first vector and the projection of the second vector along the direction of the first. Now that needs a picture to help you try to absorb that. So now let me show you the picture. Okay, try to help you understand the picture. So it's the same A and B that I showed you in the previous slide with a little more stuff added. All right, here's the vector A, just like we drew before. And then there's the vector B. But now what we're going to do is we're going to take the component of B along the direction of A. So we've got this black line along the direction of A, just extending it. And then to get the component of B along the direction of A, we drop a perpendicular from the tip of B to along the direction of A. That's that. See the right angle symbol? And the component of B along the direction of A is that component of B right there, which is just B cosine phi from the picture. So if we take the magnitude of A and then multiply it by the projection of B along A, the component of B along the direction of A, that means to multiply it by magnitude B cosine phi, but that's exactly what we defined as A dot B. So we took the magnitude of A, and then we took the component of B along the direction of A and multiplied those two things together. But you can also turn it around, just so in case you were wondering. You can start with the vector B. That's right here. And then you can say, what's the component of A along the direction of B? That is this perpendicular. Let me drop the perpendicular from the tip of A to B. See the right angle there? And this right here is the component of A along the direction of B. But that is just A, magnitude A, cosine phi. So we take the magnitude of the first vector, in this case it's B, times the component of the second vector along the direction of the first vector, magnitude A cosine phi. But that's still just A dot B. So you can think of it, if you want to, geometrically, either as the magnitude of A times the component of B along the direction of A, called the projection of B along A, or the magnitude of B times the component of A along the direction of B, the projection of A along B. That's a geometrical interpretation of scalar product. Okay, there's one more thing about scalar product that is very handy to know that I want to talk about, and then that will be all for this video. I want to now talk about an alternative version of the scalar product that is very useful to use, okay? An alternative version of scalar product that is useful when the vectors are given in unit vector notation. So I want to do A dot B, scalar product, but the A is given to me in unit vector notation. So here it is. A sub x times I hat plus A sub y times j hat plus A sub z times k hat, where ax, ay, and az stand for numbers. And then similarly, the vector b is given in unit vector notation. B sub x times I hat plus B sub y times j hat plus B sub z times k hat, where bx, by, and bz are numbers. And so I'm given the a and b in unit vector notation, but I want to do the scalar product. How do I do it? Okay, I'm going to tell you one important thing about the scalar product that I hope your mathematical intuition would say is common sense, and that is it is distributive. Okay, you have to, one by one, take each of the terms on the left and dot it into each of the terms on the right. So I'm going to write some of these out for you. For example, one of the terms you're going to get is a sub x times b sub x times, parentheses, I hat dot I hat. Where did that come from? Taking that term in the first vector, dot that term in the second. All right, that's what that is. I just put the ax times bx together. They're just numbers. And then I have I hat dot I hat. All right, plus. Now, let me take the first term in the first vector, ax I hat, and dot it into the second term in the second vector. So that would look like ax times by times I hat dot j hat. First term in the first vector dot second term in the second vector. Plus, now let's take the first term in the first vector, dot it into the third term in the second vector. So that'll give me axbz times I hat dot k hat. Now that's 3 terms, but that's not all. There are 6 more, right? 6 more terms. You should see for yourself that you can write them all out, because you got to take one by one of the terms in the first vector dotted into one of the terms in the second vector. And there are 9 different terms that come out of that. I've written the first 3 out explicitly. There are 6 more that you should practice writing out for yourself. Now what I want to do, because the first 3 is enough to show you what I want to show you, I want to talk a little bit about the dot products that are now sitting here, one by one. One of the dot products I have is the unit vector I hat dotted with itself, right? I hat dot I hat. What the heck is that? Well, let's figure it out. Remember the definition of scalar product. This is a scalar product. 2 vectors. You take the magnitude of the first vector, magnitude I hat, scalar multiply with the magnitude of the second vector, magnitude I hat, times the cosine of the angle between them when they're drawn with a common tail. What is that angle? Well, if I imagine an x-axis going to the right, isn't I hat just a little unit vector that points in that plus x direction? So what's the angle between I hat and itself? I hat and another I hat. Well, they've got to be pointing in the same direction, right? So the angle between them has got to be 0 degrees. And it's very handy to remember that the cosine of 0 degrees is simply 1. Now, what's the magnitude of I hat? I've got it twice here. What is that? That's a unit vector. Unit, that's the key word, unit vector. Do you remember? A unit vector has magnitude equal to 1. That's where the word unit comes from. So that's our each one. So this boils down to I hat dot I hat boils down to 1 times 1 times 1. 1. The scalar product of a unit vector with itself is 1. So that must also be true if you had j hat dot j hat. That scalar product must also be 1. And if you have k hat dot k hat, that scalar product is 1. That's very helpful to know. The scalar product of a unit vector with itself equals 1. How about another unit vector combination, scalar product of unit vectors that I have here, like I hat dot j hat? Well, let's do this. Let's work out the scalar product. That's the magnitude of the first vector, magnitude I hat, times the magnitude of the second vector, magnitude j hat, times the cosine of the angle between them when they're drawn with a common tail. Now let me draw an x-axis going to the right and a y-axis going up, because I hat points in the plus x direction, but j hat points in the plus y direction, right? J hat's the unit vector for the y direction. And phi, in the cosine phi, is the angle between I hat and j hat. But that's exactly 90 degrees. So this is the cosine of 90 degrees. Here it's very handy to remember that the cosine of 90 degrees is 0. And so even though these other parts here aren't 0, like the magnitude of I hat is 1, and the magnitude of j hat is 1, the fact that I have cosine of 90 makes this scalar product equal to 0. The scalar product of any unit vector with any different unit vector is 0. So I hat dot j hat would be 0. And similarly, I hat dot k hat equals 0. Or, can you think of another one? How about j hat dot k hat? 0. That's very useful to remember. The scalar product of a unit vector with a different unit vector equals 0. All right, now with all this discussion about scalar products of unit vectors, let me show you what this expression for a dot b in terms of the components of a and b simplifies to. Remember I said up there were a total of 9 terms when you distribute the dot through the two vectors? What remains when you have written all those out and looked at all those various scalar products of unit vectors? The result's got to be a scalar. There can't be any vectors anywhere in the final answer. And it simplifies to the following pretty basic result. Take ax times bx plus ay times by plus az times bz. This is very useful. Okay? Notice no vector symbols on the right side. No arrows of any kind, no hats of any kind. The result is a scalar product. And all you do is take the product of the two x components and add that to the product of the two y components and add that to the product of the two z components. And you will have the scalar product. And yes, that will be the same thing that you would get if you had enough information and you did all the math right, if you took the magnitude of A times the magnitude of B times the cosine of the angle between the A and the B. The way we define scalar product to begin with. That's still true. But what I've shown you is an alternative way to calculate that, the handy way to do it if you're given A and B in unit vector notation. Okay, so that's kinetic energy and scalar product of two vectors. We're going to use both. For the rest of this chapter, we're going to use them a lot. So there'll be another video here where we're going to introduce the concept of work. That's all for this video, though.